Welcome to Lecture 10 of Modeling and Simulation of Physical Systems, in which I shall introduce you to the modeling techniques for the electromechanical systems. The lecture agenda items primarily include the model of the DC electrical motor and the amplifier controller, which is acting as the driver circuit for the DC motor. In addition, we shall also look at the models for the tachometer and the encoder. These are basically the components to provide feedback concerning the speed as well as the position, the angular position of the motor. And using these components, we shall compare the transfer functions of the DC motor speed control, the one without feedback, and the DC motor speed control with the feedback. And in the end, we shall also discuss in detail the DC motor position control that necessarily comes with the feedback of the position of the motor. Let us look at the model of an electrical DC motor. The model can be thought of as a composition of an electrical motor of the stator windings and the mechanical motor of the rotor. The input to the electrical circuit that describe the stator winding is either the voltage, the supply voltage, or the current, supply current IM. So we call the input to the motor model as the voltage, that will be the motor supply voltage, or the motor supply current IM as shown here. The output are the dynamical properties of the rotor, such as the torque or the speed. So omega m, showing the motor angular velocity, can be one of the outputs, just as the torque applied to the rotor, or the torque that is generated inside the motor, and then the torque is then transferred to the load that a motor is supposed to rotate. This model is suitable for a large variety of DC motor, even if the actual hardware composition is slightly different. And it is generic enough to include multi-phase motor systems such as three-phase brushless DC motor. Furthermore, we are going to make some simplified assumption for our remainder of discussion. That is, first of all, the motor inertia is deemed negligible. In other words, we're saying that the inertia of the cylindrical part that is used to model the rotor, that is zero. Secondly, we shall assume that the stator winding has negligible resistance, hence RS is equal to zero. It's negligible. Moreover, we shall assume a linear relationship between the torque that is generated inside the motor and applied to the rotor, that is Tm, is proportional to the supply current Im. Likewise, the rotor speed, which is essentially the same as the motor speed, is directly proportional to the back EMF voltage EB, which is the voltage generated across the terminals of the inductance of the stator windings. Because of these linear relationships, the constant of proportionality in case of the torque and the current relationship is kT, the torque constant, and in case of the relationship between the supply voltage EM and the speed, this is actually derived from the speed, the motor speed. We know that this is proportional to the back EMF, that is KE. The actual relationship is KE times omega m equals to EB, but because we have assumed that the stator winding resistance is zero, so EB is same as EM. In other words, we are going to say that the supply voltage is directly proportional to the motor speed. That's because Rs is equal to 0. Further simplification requires us to assume that the two torque constant, that is the two motor constants Kd, which is the torque constant, and Ke, which is the speed constant, they are both equal and they are set equal to K. In the nutshell, the motor model is basically described by these two relationships, which relate current with the torque as a linear relationship, and also the speed, the angular speed or the angular velocity, being taken as proportional to the supply voltage. Next comes the model of an amplifier controller, which is used to model the driver circuit of the DC electrical motor. The main job of the amplifier controller is to supply a suitable amount of voltage to the stator winding. So in this case, V out will be connected to the input terminals of the stator windings. The current drawn from the amplifier is I out, which is going to become the motor supply current. In this sense, both the I naught and V naught are the inputs to the DC motor. The amplifier controller circuit is an op-amp based circuit which is connected in a negative feedback configuration. As you can see here, the output of the op-amp is V naught, which is being fed back through the to the negative terminal over here with the help of a resistance R2. The other end of the negative input terminal is grounded to the resistance R1. The input to the amplifier controller is a voltage signal V in, which is fed to the positive terminal. Such an amplifier controller circuit is used when there is no external feedback signal that is subtracted from V in. We're going to use this amplifier controller circuit in the control of DC motor speed, or the angular speed, or the angular velocity when there is no feedback. It is particularly easy to solve this circuit and develop the model that relates the input voltage with V out. But before we do that, we should notice there is some resistance which is connected between the output of the op-amp and the terminals over here which are connected to the stator windings. This R naught accounts for the amplifier output resistance. So in our discussion of the electromechanical systems, we are not going to ignore the amplifier output resistance. In fact, it is going to play a crucial role in the final expression, the final differential equation of our interest. Therefore, if we solve this circuit, we are first going to relate the output of the op-amp V naught with V in, which is going to be 1 plus R2 over R1. That's because the op-amp circuit is connected to implement a non-inverting amplifier. We can call this quantity as the gain, G. And this gain is multiplied by the input voltage to give us the voltage at the output of the amplifier, and subtracting I out times R naught, that is the voltage drop across the amplifier output resistance. If that is subtracted from V naught, we're going to get V out. There is, however, another version of an amplifier controller circuit which amplifies the difference of the two input voltages applied to its indirectly applied to its positive and the negative terminals. In this case, we say that one of the two input voltages is V in, and the other one is VF. And the final expression that we are going to develop is eventually going to amplify the difference of V in and Vf in the form of V in minus Vf times the gain. The expression for the gain in this case will be slightly complex, as we shall see in our discussion. And once again, the output of the amplifier controller is going to be fed to the input of the DC motor. Such an amplifier controller is particularly useful when we want to amplify the difference between the two inputs. So in this case, we have input V in and the other input is Vf. And the interpretation of Vf is that the other input, the additional input in this case, Vf, actually comes from some kind of a feedback describing either the position of the DC motor or the angular speed of the DC motor. And we wish to amplify the difference for the further control. Now, understanding this circuit is not that difficult. Again, we have a negative feedback op-amp based circuit. So the output of the op-amp is fed back to the negative terminal with the help of resistance R3. The other end of the negative input terminal of the op-amp is connected to Vf, the feedback voltage, with the help of resistance R1. On the positive input terminal, we have a voltage divider circuit. So whatever voltage V in is applied over this terminal is divided between resistance R2 and R4, and the voltage across R4 will be appear at the positive input terminal of the op-amp. And if we solve this circuit, we get an expression of the op-amp output voltage V0 related to the input voltages V in and Vf. But note that the coefficients of the voltages are different. The coefficient of V in is R4 divided by R2 plus R4 over here, and this is multiplied by R1 plus R3 divided by R1. And if we compare this with the coefficient of the other voltage, Vf, that is R3 over R1. However, if we impose a restriction saying that R1 plus R3 is equal to R2 plus R4, we can actually cancel these two terms, and the coefficient of V in becomes R4 divided by R1. And the coefficient of Vf is still R3 over R1. However, imposing another condition saying if R4 equals to R3, then the two coefficients become the same. In this case, G will be equal to R3 over R1, which is same as R4 over R1. The output of the amplifier controller must subtract the voltage drop across its output resistance R0. Therefore, we say that V out is the amplified difference of the two input voltages minus the voltage drop across the output resistance R0. So once again, it is reminded that this version of an amplifier controller is used whenever we wish to have a negative feedback in the system, which is essentially another voltage input such as Vf, which is going to be subtracted from the main input or the reference input V in. Alright, so let us look at a first example. We call it an open loop DC motor speed control. So the word open loop really refers to no feedback, meaning that if a motor is being run on a specific speed, and if there are some external disturbances or even if internal disturbances, then there is no way that we can record those disturbances and have them cancelled out. The circuit of this electromechanical system contains an amplifier controller, shown here, driving the DC motor, whose shaft over here is connected to some load, shown as a disc here. And the load has some inertia, represented as J. The load also experiences some disturbance torque TL. We say that if the DC motor is rotating in one direction with some angular velocity omega m, and if we make an assumption that the motor is rigidly connected to the load over here through a rigid shaft, so we're assuming that there is no twist in the motor shaft, then the DC motor is essentially coupled to the load. So whenever there is an external disturbance torque TL that is applied to the load, that whose effect of this external disturbance is going to be reflected to the motor. So our modeling assumption, we say that motor shaft is rigid and it has zero inertia. The other assumption is that the load experiences some disturbance torque TL, and the load also experiences the motor torque Tm. So motor torque is a torque that is responsible for rotating. So let me show it with the help of this arrow. This double arrow will be the direction of the motor torque. Essentially, the motor torque is generated over here inside the rotor, but because the rotor inertia is negligible, that torque is transferred to the load, considering the fact that the motor, rotor, and the load, they are coupled mechanically. So here is the further description of the electromechanical system under discussion. Inside this DC motor, the mechanical part of our interest is the rotor, whose inertia Gm is taken equals to 0. As described earlier, the motor torque Tm, the torque that is generated inside the motor due to the interaction between the stator and the rotor magnetic field, is a torque Tm that is responsible for the motion of the rotor, shown as theta m. The corresponding angular velocity would be omega m, that is just theta m dot. And the rotor is rigidly connected to the load with the help of a massless shaft, and the shaft is rigid. Over here, we reiterate the fact that because the rotor and the load are coupled, so whatever torque is applied to the rotor is being transferred to the load over here. So the final simplified representation will be the load experiencing two opposing torques, one applied by the motor and the other being the disturbance torque in the opposite direction. And the angular displacement variable of the load is the same as the angular displacement variable of the motor, that is theta m. That's because the load is mechanically coupled to the rotor. The other assumption going into our model is that Tm and Tl are not the only torques which are applied to the load in our electromechanical system. In fact, there is some friction, the frictional torque, that is being experienced by the rotor. And because rotor is mechanically coupled to the load, so whatever frictional torque that the rotor experiences is the same as the frictional torque experienced by the load. that is modeled by means of a rotary damper whose damping coefficient is capital B. So the complete model, the mechanical subsystem of our electromechanical system, is the inertia, load inertia experiencing the motor torque, the disturbance torque, as well as the torque due to the rotary damper whose damping coefficient is B. That is the complete description of the mechanical subsystem under discussion. Once we have completely specified our modeling assumptions, we are now ready to describe the main problem that we're trying to solve here. The problem asks us to develop a differential equation between the two inputs of the systems. What are those two inputs? Well, the first of them is the disturbance torque experienced by the load, and the other one is the supply voltage that is fed to the amplifier controller, ED. We are supposed to relate the two inputs with the output, which is taken in this case at the speed. That's because it is a motor speed control problem. You can call this speed or you can call this angular velocity. Both terms are essentially interchangeable. So we are going to relate the speed of the motor with the two inputs, disturbance torque and the supply voltage, ED. And with the help of that differential equation, we shall then try to find out the expressions of the time constant, the static gain, which is the partial derivative of the speed with respect to the supply voltage when the derivative operator is set equals to 0, that is capital D equals to 0. And finally, a very interesting parameter known as the disturbance sensitivity needs to be calculated, which is the partial derivative of the motor speed with respect to the partial derivative of dl. Essentially, the disturbance sensitivity describes us, it reveals that how sensitive is the motor speed to the external disturbance torque, dl. So we are going to write down the modeling equations in a systematic manner. So if we start from the left hand side of the system, we find the amplifier controller whose input is ED and the output is the voltage at the input of the DC motor and the current entering the DC motor, EM and IM respectively. This first equation will be the equation of the amplifier controller without feedback. So there is only one input, that is ED. The other part of the problem is the modeling equation that accounts for the electromechanical relationship for the DC electrical motor. In this case, we know that the motor torque is K times motor current and the motor speed is 1 over K times EM, the supply voltage. So we have seen those equations before, so we are writing them down explicitly over here. Then comes the load. For that, we can easily write down the torque balance equation based on the Newton's second law of motion. So the motor torque Tm that is being transferred to the load inertia is in the direction of displacement, that is theta m, or in this case we are basically interested in representing the equation of motion in the form of the angular speed omega m. Therefore, the equation will become Tm equals to j omega m dot. Omega m dot represents the angular acceleration, just remember that, plus beta times omega m plus disturbance torque TL. Four equations are sufficient to develop the differential equation of our interest, but not before some simplifications, namely the algebraic simplification, particularly in terms of representing the derivative of the velocity in terms of the derivative operator capital D. So remember, d omega m is essentially the same as omega m dot. So we can rewrite equation 4 in terms of the derivative operator. And we have done this several times before. Let's do that for equation 4. And then further algebraic simplification can be stated in the form of following steps. Eliminate the torque, motor torque Tm from equation 4. And that is done by first expressing the motor torque in terms of motor current given in equation number 2. So when we try to eliminate the motor torque, we introduce the expression of motor current Im. But that also needs to be eliminated. This is done by substituting the expression of Im given in equation number 1, the amplifier controller equation. So once that is attained, express Im as G times Ed over omega m over R naught, a whole divided by R naught. And we're just going to put that into equation number 4. Which, upon further simplification, will give us a first order differential equation shown here. If we note that this is a first order system, because we have in the denominator we have only one derivative operator. In the numerator we have the two inputs with corresponding weights given here, and all the terms have common denominator small d. This is 1 plus p times R naught divided by k square. So that is written out separately. This is the desired differential equation. However, we are also interested in looking at some of the parameters of our interest, such as the static gain. Static gain is defined as the partial change, or the rate of change of motor speed with respect to the change in the supply voltage. That is, the static gain measures how sensitive is the change in the speed, or how sensitive is the speed with respect to the changes in the input supply voltage. So if we change the supply voltage, then how quickly the speed of the motor is going to change. That is the partial derivative of speed with respect to partial derivative of the supply voltage, calculated when the rate of change is 0. Because the rate of change is 0, that's why I call this a static gain, also known as the zero frequency gain, because the rate of change is 0. We want this to be as high as possible. So higher static gain, the better it is. And that's because we want our speed to be more responsive to the change in the supply voltage. In other words, a small change in the supply voltage, a small change over here, can give us a large change in the motor speed. So here is the expression for the static gain. And you can see that one can easily increase the static gain simply by increasing the gain of the amplifier, or reducing the output resistance of the amplifier. The other parameter known as the disturbance sensitivity, which is a measure of sensitivity as far as the speed of the system is concerned with respect to the disturbance torque TL that is applied to the load. So we are interested in knowing how easily the disturbance torque TL can affect or can cause changes in omega m, the motor speed. And because we don't want external disturbance to change the motor speed, that's because we want to keep the motor speed constant. Therefore, any change in the speed is highly undesirable when the agent of the change is external disturbance. Therefore, we say that the disturbance sensitivity lower magnitude wise, obviously, as we should see that the sign, it comes with a negative sign. So magnitude wise, lower disturbance sensitivity is better or desirable. That is partial omega m with respect to partial TL when the rate of change is set equals to 0. The expression turns out to be this. Because we wish to reduce the magnitude of the disturbance sensitivity, we can see that with increase in motor torque constant or the speed constant, one can reduce the disturbance sensitivity. So if K is large, then disturbance sensitivity will be lowered. What about, there's another way. You might want to think of other ways to reduce the disturbance sensitivity, one that doesn't require us to change the parameters of the motor, because that's our hardware. It might be difficult. Try to think about this question. How about if we try to reduce R0, increase R0 to reduce the disturbance sensitivity? But the problem is that R0 appears not only in the numerator but also in the denominator. So that might be a little bit tricky in this case. Finally, the time constant of the system. We know how to compute the time constant of the first order system. Time constant defines the time it takes for the speed to reach its steady state value, reach 63% of its steady state value. So for example, if we want our speed to reach at this level, omega m, so that if this is some threshold where the omega m, the motor speed, needs to attain, then we know that the speed of the motor is not going to instantaneously reach its steady state value. Rather, it is going to take some time, and this time tau over here, which defines 63% of its maximum value, 63%, that defines the time constant. So how do we find the expression for the time constant? Well, we just look at the denominator and identify the coefficient of the differential operator d. So the time constant is nothing but JR0 over K, this guy over here. So that is the time constant. You might be wondering that this is a first order system, but in terms of two inputs. So you can write this as the difference of the sum, weighted sum of the two first order system transfer functions, but in both cases the coefficient of the d is the same. So we want this time constant to be as small as possible. We want the motor to attain its steady state speed as quickly as possible. So lower time constant is what is desired over here. And what are the ways to reduce time constant? Well, obviously you can see that because the load inertia J is appearing in the numerator of the time constant expression. It is actually the time constant because it is proportional to J. So if we can reduce the load inertia, then time constant will be reduced. But sometimes it is not possible to reduce the load that the motor is supposed to rotate. So alternatively, we can reduce the amplifier resistance R0, but then again it also appears in the denominator, so we'll have to be a bit careful. The other possibility might be increasing the motor time, torque, and the speed constant, but again the same problem. It appears in both the numerator and the denominator. So that tells you the complication behind reducing the time constant of the motor because a lot of the parameters which we wish to tweak appear both in the numerator and the denominator. So at this point, we're going to take a pause and think about a way to simultaneously reduce the time constant as well as disturbance sensitivity, the two parameters, the performance parameters of the DC motor speed control. We want our motor to be less responsive to the disturbance torque TL, but more responsive, and we also want it to reach its steady state value as quickly as possible. The other requirement is that we want our motor to be more responsive to the input. So this ED is a good guy, and we want our motor speed to be responsive to ED, but more responsive to ED, and this is a bad guy, TL. So we don't want our motor speed to change much when there is external disturbance torque. These requirements are actually conflicting in nature because, as we saw, there are system parameters such as the amplifier output resistance, the load inertia, the motor speed and the torque constant, etc. And it seems difficult that we can simultaneously achieve these conflicting requirements that easily. But anyways, let us try to figure out a possible solution, a possible approximate good solution, if not the best solution. And what are the techniques to improve the performance of this open loop DC motor control system. An interesting observation is that the three performance matrix, the time constant, disturbance sensitivity, and static gain, can be simultaneously lowered simply by increasing their common denominator, d, 1 plus br naught divided by k square. And that can be done by adding to it a non-negative quantity. This is going to be worth a trade-off because 2 out of these 3 performance metrics we want to have a lower value. So we want to have small value for the time constant, small value for the disturbance sensitivity, although we want a high value for the static gain. It is going to be a valuable trade-off because we care more about the time constant and the disturbance sensitivity. And we can compensate for the lower static gain simply by increasing the supply voltage. So how can we add a non-negative quantity to the common denominator? So remember, this common denominator appears as just a common denominator in the expression of all 3 performance metrics. How can this be done? The solution is particularly simple by adding the feedback of motor angular velocity. So we are going to extract the information of the motor instantaneous speed and we are going to feed it back to the input side. In fact, we are going to bring it into the amplifier controller, have it subtracted from the input input voltage to the amplifier controller. Now, for the purpose of feedback, we mount some kind of angular speed sensor or a component that can sense the angular speed. That can be either a tachometer or an encoder, shown here. So in case of an encoder, it is just like a very thin sleek disc that can be mounted on the motor shaft as shown here in blue. And the output of an encoder is an electrical signal EF that is going to become the second input to the amplifier controller, and this is going to become the input, if you remember VF, the other input, and this ED is the main input VM. The amplifier controller is going to amplify the difference of ED minus EF. In other words, this amplifier controller is now a differential amplifier controller over here. And when the output resistance of the amplifier is taken into consideration, we subtract the voltage drop from the amplified signal, which is the amplification of the difference of the two signals ED and EF. The assumption about the motor encoder can also be extended to model the tachometer. In any case, the output of the motor encoder is taken as directly proportional to the speed of the motor omega m. We can just say the constant of proportionality is h, also known as the encoder gain. It remains unlabeled over here, but that's what it is labeled in the textbook. The h is known as the encoder or the tachometer gain. So EF is h times omega m, where h is constant. Just remember that it is a constant quantity. Also, the other important assumption is that the encoder inertia is negligible, meaning that the disk over here has negligible mass, negligible inertia, therefore its dynamics are not taken into consideration. And all other assumptions remain unchanged. That is, the assumptions we made about the load and its disturbance torque and the friction effect experienced by the rotor and the displacement variable associated with the DC motor all remain the same. A quick recap of exactly what we are trying to achieve is summarized here. We want our motor to attain its speed, the desired speed, as quickly as possible. So for that, if we can plot this motor speed omega m profile as a function of time, and suppose this is the target speed, and this target speed, and this is specified by the motor supply voltage, which in turn depends on ED. So if this is the target speed, then we want the motor speed to raise its value from 0 to attain the target speed in as short a time as possible, and that time is quantified by the time constant tau, which is essentially the 63% of the target speed, as we know. Now once the motor is running at its steady state angular velocity as shown here, then our other requirement is that related to the disturbance torque. So for example, if there is some disturbance torque applied when the motor is running at its target velocity, as a consequence, the motor speed is going to change abruptly for the period when the disturbance torque is non-zero. And this is a significant dip in omega m. And this is bad. We want to improve the response of the system by reducing the amount of this dip. We want to reduce it to as small a value as possible, such as only this. This is desirable. So this change in the speed is what, a small change in the speed is what we want to achieve with the help of feedback. So that is, how do we obtain such a response? Well, the solution is in the form of feedback. We are going to take a feedback of omega m. So in the feedback-based DC motor speed control, this is no longer an open loop system. Rather, this is going to be a closed loop DC motor speed control system. It is a closed loop because this loop, as you can see over here, this loop has been closed. The output has been fed back, so this essentially constitutes the loop. Then the consequence of this feedback is, if for example the motor is running at low speed than what's needed, then the difference between ED and EF will be large, and therefore this EM will increase, and that will in turn increase the speed of the motor. On the other hand, if the motor speed is low, or if the motor speed is too high, if this is too high, then the difference ED, EF, the difference between the two will be smaller, and the amplifier controller gain is so set that EM is going to reduce, and this will in turn bring the motor speed down to some small value or lower the speed of the motor. The modeling equations of the systems are more or less the same as before, especially the torque and the current relationship, the relationship between the motor speed and the motor supply voltage, the mechanical dynamics of the load, inertia. The only thing that changes is first the equation of the amplifier controller, which is now amplifying the difference of ED and EF, where EF is a feedback, motor speed feedback signal. So this is the new quantity which is being introduced into the equation. The other change is the model of the encoder, which says that the output of the encoder is proportional to its speed. This is written as a new equation. It should have been equation number 5. Combining the 5 modeling equations, this really should have been equation 1 through 5, and then can be simplified to the final expression as shown here. The final expression adds only one new term, which is not this term. This is not the new term over here. In fact, this is the new term which has been added to the left hand side, GKH divided by R naught. As a consequence of this addition, the final expression that relates the motor speed with the inputs ED and TL has one modification, that is the common denominator now changes to D prime, and D prime is just 1 plus BR naught divided by K squared, which is same as before, plus this new term. So that's the new thing, new term that has been added, and it is a non-negative term. The gain is non-negative. The amplifier gain as well as the encoder gain, they are both non-negative, and the motor torque and the speed constant, they are non-negative. Consequently, with the help of a feedback, we have been able to increase the common denominator by adding to it a non-zero term, that is GH over K. And because the common denominator has been increased, so that is going to lower the time constant. That is, the motor now reaches its target speed in a shorter time, and also it is less sensitive to the external disturbance torque. So both values have been lowered successfully. But what about the static gain? The common denominator has been increased, therefore the static gain will also reduce. But this is an undesirable change. So in fact, we have reduced the time constant, we have reduced the disturbance sensitivity at the cost of reduced static gain. So that is a trade-off, that the feedback has lowered the time constant, disturbance sensitivity at the cost of lower static gain. We say that this is still worth a trade-off. And why is that? Well, that's because we can compensate for the lower static gain value by increasing ED, which means that we are now going to pump more power into the system. So the ED increases. As we increase ED, then obviously that is going to increase the voltage, the applied voltage to the system, and therefore it may likely require us to pump more power into the system. So the feedback system that we wish to operate may need more voltage for the power. Our last example is that of a DC motor position control system. Such a system finds a lot of application in mechatronics engineering, particularly in the field of robotics, where we want our robot joints to obtain respective angular displacement at any given time. The input to the system is again a voltage which is now specifying the desired position, the desired angular position, that is theta d. So remember, theta d is a voltage that specifies the desired angular position of the motor. In the context of the DC motor position control and their application, they often come with the gear system, or we attach a gear system with the motor, because in the position control application, speed is not a requirement. In fact, we want a reduction in the speed and we want a higher torque. So in other words, when we talk about the position control, we are indirectly looking for a higher torque for the given application. So the torque requirements are typically higher in the positioning control system. In this problem, we have added a gear system to the motor, as shown here. And the motor is driving the load through the gear system. So in summary, the goal of the position control system is to be able to precisely control the angular displacement of the DC motor with the help of gears. Such a position control system necessarily comes with a feedback or requires feedback. In this case, we're going to take feedback with the help of a motor encoder. And as described earlier, the desired angular position is now specified in terms of the input voltage theta d, which is the input applied to the amplifier controller. However, at this point, I should clarify that the position control system does not always require the addition of gears. In fact, position control can be accomplished without the addition of gears. But because in a typical application of motor position control, we find the gear system attached with the motor, therefore in our problem, the gear systems have been duly included. Students are welcome to redo this problem without including the gear system and by directly attaching the motor shaft with the load inertia. All right, then, what are our assumptions over here? The amplifier controller is accepting two inputs, the one describing the desired angular displacement theta d, the other one is the motor position information captured by EF. So the encoder model is now changed. It is now describing the position of the motor, and that position is um, indirectly measured because we have now introduced the gears between the motor and the load. The angular displacement at the larger gear is theta. That information is fed back into the system by means of an encoder. So EF is equal to h theta, where theta is the angular displacement of the larger gear. The smaller gear is mechanically coupled to the rotor of the DC motor, and it has a different angular displacement variable theta m. And we shall explore these displacement variables in more detail in a bit. But first of all, let us summarize the other important modeling equations, such as the motor torque with the current relationship between the motor torque and this current. It remains the same. So is the relationship between the angular speed of the motor with the EM, that is the supply voltage. We can also say that angular speed is the rate of change of angular displacement theta m. So that is k times omega m is k times theta m dot. Now comes the tricky part of this problem, that is the model of the gear system. The speed ratio Rs is defined as the ratio of speed of the larger gear, that is theta, to the speed of the smaller gear, that is theta m. So we say that Rs is theta dot divided by theta m dot. But if you take an inverse of this speed ratio, you get a gear ratio, which is written as n theta over nm. So n theta is the number of teeth on larger gear. It's the number of teeth on the larger gear. We're talking about the number of teeth on the larger gear, this one. And the other quantity is nm, this guy. And m is the number of teeth on the smaller gear, small gear. That is, we're talking about this gear, the small gear. Additionally, we shall assume that there is some viscous damping experienced by the gear system. And the viscous damping is being modeled by means of a rotary damper whose damping coefficient is capital B. That damper can be attached either to this larger gear or to this small gear, but schematically it is much easier to attach a damper to the smaller gear because the larger gear is connected to the load inertia by means of the rigid shaft. So remember, we shall roll out the modeling assumption about this shaft, but this is a rigid shaft. Maybe it is worth mentioning it over here. It's a rigid shaft and it has zero inertia. So we have attached a damper to the smaller gear. We could have also attached it to the larger gear, but would have been much more complicated to represent. Also, as described earlier, the rotor of the motor is coupled to the smaller gear, as shown here. So the rotor is mechanically coupled to the smaller gear by means of a rigid shaft. Again, it has zero inertia. All the shafts have zero inertia. They are rigid. And because the two mechanical inertias, the inertia representing the smaller gear and the rotor inertia, they are mechanically coupled. So we can shift this damper further leftwards over here because at the end of the day, both these inertias, the rotor inertia and the smaller gear inertia, are going to add it up. It's because they are mechanically coupled. So there is no harm in further shifting this damper leftward. And again, we'd reiterate that the rotor inertia is taken equals to 0. The shaft inertia, the inertia of all the shaft is set equal to 0. And proceeding further, let Jm be the inertia of the smaller gear and J theta be the inertia of the larger gear, shown here. Now, one of the things that is missing, that has been missing so far, is the description of the torque generated by the motor, Tm. So Tm is the torque that is generated by the motor, and it primarily acts on the rotor, as shown here. So the rotor torque, the torque applied to the rotor, is causing this angular displacement theta m, and they are both in the same direction. As a result, this torque which is applied to the rotor will be transferred to the smaller gear because the rotor and the smaller gear are mechanically coupled, as described here. So in the simplified version of the diagram, we are going to eliminate the rotor inertia altogether, and the shaft connecting the rotor inertia with the smaller gear, and we're just going to say that the motor torque is directly applied to the smaller gear. Let the radius of the small gear is Rm and that of a larger gear is R theta. And we now connect the damper back to the smaller gear as was done initially, and there is no further change in the other part of the system, the mechanical subsystem. So right now we are unrolling our assumption about the gear system as well as the load which is attached to the gear system. Now at this point, I would like you to recall how we modeled the gear system where we assume that the two inertias are in contact, and there is a frictional force F which is pushing the larger gear in one direction and the smaller gear in the other direction. The two modeling equation can be written as follows. Part of your homework exercise, you're required to show that the two equations can be simplified and merged into one equation that relates theta, the angular displacement of the larger gear. That's what we are interested in controlling. So theta, so differential equation that relates theta with the motor torque Tm, this quantity, and the disturbance torque TL. So these are the two inputs. You can consider these as the two inputs with the output theta. And here is the equation that I have developed, and this is what you're going to validate by means of your homework exercise. We have expressed, so the right hand side of the equation has the coefficient of the motor torque, that is n theta over nm. What is that? Well, that is just the ratio of the number of teeth on the larger gear to the number of teeth on the smaller gear, which is same as the radius of the larger gear divided by the radius of the smaller gear. That is the same as Rs, or 1 over Rs to be specific, 1 over Rs, the gear ratio. Finally, another assumption, in fact yet another assumption, we are going to assume that the gear inertias are also negligible. Therefore, we're going to set J theta and Jm equals to 0, which will significantly simplify our equation, in which J theta and Jm terms will be set equal to 0. The final expression is shown here. And there is no other torque or force that is acting on our gear, motor, or the load. So that after this equation, there is we have accounted for all the torques and the forces, and there is no other force or torque or loading that is being applied as far as the mechanical subsystem of the DC motor position control system is concerned. Quite naturally, in this case, we are going to have more equations, as many as 6 of them. So let us look at those equations. The first of them is going to be the equation of the amplifier controller over here. It is again used as a differential amplifier. In this case, we are going to subtract EF from C times theta D. So a constant has been introduced, C, which is not very difficult by just changing the resistances inside the controller amplifier. So remember, there were some resistances R1, R2, R3, R4, and we ensured to have we set those resistances such that C was equal to 1. But you can very much tweak those values, and you can have C that is not equal to 1. And later on we shall see the significance of introducing this constant C over here as well. Gain times the C theta D minus EF minus the voltage drop across the output resistance. The encoder model says that the output of the encoder is proportional to theta, and the relationship between the motor speed and the speed at the output gear, the larger gear, is just theta m dot is equal to theta dot divided by rs, the speed reduction relationship, the two familiar motor equations, and finally we have the dynamical equation as far as the mechanical part goes, shown here. We are supposed to utilize all these three equations to eliminate Tm, Im, Em, theta m to form a differential equation that relates theta with theta d, one of the inputs, desirable inputs, and the other input TL, which is undesirable. And we can manipulate those six equations and do some algebraic simplification and obtain expression as shown here. The final expression of the theta with that relates theta with theta d and theta and TL is going to be a second order system as shown here. And again, we have a common denominator, small d, which is G times K times H divided by R naught RS square. So students are encouraged to drive these equations, the three equations defining three equations to obtain the end result shown here. It's a bit of an algebraic simplification, hopefully not that difficult. And then from this equation, we are required to find the expression for the quantities such as static gain, a familiar quantity, and a new quantity known as the static stiffness. What are the expressions, corresponding expressions? Static gain is the rate of change of theta with respect to the change in theta d when the rate when the differential operator is set equals to 0. So static gain describes how quickly the theta changes with respect to the input displacement, in reference displacement theta d. So that looks familiar, except that the static gain now relates theta, the output displacement variable, with the input displacement variable. But what about this new term, static stiffness, Ks? Well, this seems something interesting and relevant to the disturbance sensitivity, but it is the change in TL with respect to theta and not the other way around. What does this static stiffness represent will be described shortly. But first of all, we shall derive their corresponding expression. So static gain, the expression turns out to be C over H, right? So that's where C becomes interesting. Thus we can say that if we want to increase static gain of the system, then we might wish to increase the value of C. That's by adjusting the resistances inside the amplifier, which is not that difficult. Now comes the interesting part, the static stiffness expression, GKH. The first thing to note is that static stiffness in terms of magnitude, higher the better. Over here we say higher the static stiffness, the better it is. And well, why we want it to be higher? Well, it describes how strongly a DC motor is capable of holding its position. So in the position control system, we want this theta to be as close to theta D as possible all the time. So as the reference position changes, the motor is rotated so as the angular displacement available at the output of the larger gear is essentially equal to theta D. But how strongly can it hold on to its position in response to the external disturbance? So as before, the external disturbance will try to deviate theta from theta D. That's what the external disturbance does. And so the static stiffness really is a measure of the resistance offered by the motor to the external disturbance. So that's why higher the better, and it can be increased by raising the amplifier gain, or if you can have a higher motor torque on the speed constant, but more importantly, higher gear ratio. So a stiffer system, a stiffer position control system should have a higher gear ratio, and that's why that describes one of the reasons why we wish to increase why we wish to introduce the gears in the position control system. An interesting observation over here is that despite the fact that the system does not contain any spring, it still shows stiffness. And why is that? And that's because the stiffness is virtual. You can call this a software stiffness, and it is a consequence of the feedback. So this virtual stiffness is a consequence of the feedback. The system as a whole we can say that the system as a whole is acting like a spring, which is trying to restore its position to its mean value. The system as a whole is acting like a spring, which is trying to restore its position state to its mean value. And the other expression, because it's a second order system, the expression for the natural frequency and the damping ratio are also given in the textbook, and students are encouraged to derive those expressions from the differential equation and match those with those given in the textbook. Also, as part of your homework exercise, please repeat the same modeling procedure for the DC motor position control without neglecting the gear inertias and find out the differential equation with non-zero Jm and J theta. So these are not going to be zero. So you're supposed to find out the expression with non-zero gear inertia. This brings us to the end of our lecture. I hope there was a lot of stuff for you to learn, new stuff, and hope you enjoyed this lecture. And I suppose you are going to have a lot of question and answer sessions. And for that, we are going to have our regular Q&A session on Thursday afternoon starting at 2 p.m. Till then, stay safe and have a nice day. Thank you very much.